So we have here an electromagnetic swing. Sean sets up another demonstration called the electromagnetic swing. It comprises a wire loop hanging between two magnetic poles as shown in the picture below. The magnetic field strength is 2 teslas. The left side of the loop X is connected to the negative and the right to the positive, I guess. And we're going to scroll down. The picture's kind of helpful if you've never seen something like this before, but you should really be able to work out what's going on if you study this. Describe and explain what happens when Sean closes the switch. So describe and explain is two things. Describe, you would see the pendulum, do they call it the pendulum? The swing. See the swing move, and it would move, since we've got current flowing in that direction through it, the right hand slap rule gives the thumb in the left hand direction, the field going downwards north to south, which means it would experience a force coming out the front. So the swing would move out the front. And explaining why that happens is because of the right hand slap rule. Gives the direction of a force, and that force is due to the magnetic interaction with the magnetic field, the fixed magnet. So B field fixed is interacting with the magnetic field on the wire, and that's the cause. The right hand slap rule gives the direction. Carrying on, B. The circuit, including the wire loop, has a resistance of 1.8 ohms. The battery voltage is 6 volts. The force on the wire is 0.25 newtons. Show that the length of the horizontal wire is 3.8 centimeters. Again, show question. So your aim is this, but you use it to check. You don't substitute it in. So the equation that relates is F equals B. Oops, B is not a V. B-I-L. We don't actually have I, because we're trying to find L. We have F, we have B. Do we have B? B should be up there. Yep, 2 teslas. And we don't have the current, but we do have the resistance and the voltage. I equals V over R, because there's the V, there's the R. So you can substitute that into there, rearrange for L, and solve. And that should give you 3.8 centimeters. Carrying on, Sean replaces the battery with a sensitive voltmeter. He pulls the loop back and releases it so that it swings through the magnetic field as shown in the diagram below. So now, instead of this being like the motor effect, a force on the wire, you are applying a force to the wire. This one is coming from the force due to gravity, swinging it through the field. And we're probably inducing a voltage or current. I think that's how it's going to work. Name the type of particle that moves inside the wire and state the direction it moves. So it's an electron, because positive charges come from the fixed nuclei, which are positively charged. And we've got an arrow here showing it swinging forward. So if we consider a single, there's 2 ways to do this. I'm going to consider a positive charge in the wire, an imaginary positive charge, to find which way it would move. It has a direction of movement in this way, which is conventional current, and north to south is downwards still, so it would experience a force on the positive charge to the right. That means the electron would move to the left. So electron moves left. Okay, and you need to, if you didn't follow that process of how I worked it out, you need to go back and look at your right hand rules for charged particles in the field. Oh, last one. At one time, the induced voltage is 11 millivolts. Calculate the speed of the wire this time. So V equals BQV. Sorry. And so 11 millivolts we have. We have the magnetic field strength of 2 teslas. And if we consider a single electron of charge 1.6 times 10 to the minus 19 coulombs, we can rearrange for the velocity V to get voltage over BQ, or in that case it would be BE, because the charge on an electron is called E, and it's negative, but the negative doesn't matter because that's just the direction. So yeah, I'm pretty sure that covers it. There's no more questions. That was wonderful.